All right, so today we will start into some real physics now that we've kind of gone through and reviewed mathematics and discussed a little bit about vectors. And so, in order to start, we must understand that the most fundamental study of physics we're going to go through is what's called kinematics, which is basically the study of the motion of objects. And we're going to eventually come up with a list of equations which relate the different variables which are involved with this motion and allow us to make predictions given a certain set of initial conditions. A car starts at 0, it starts from rest. It accelerates for a certain period of time. How fast will it be going after that period of time? Things like this. These are the types of questions we will eventually be able to answer. However, before we get to that, of course, we need to know what are those important variables. What are the important concepts to know when it comes to a topic like kinematics? Well, there's actually only a few things you need to know. First thing is called the position. And it's usually denoted by the variable x. And it basically describes where an object is in space. When we discuss objects, when we discuss systems, of course, we're allowed to talk about them in any number of dimensions. The real world, of course, consists of 3 spatial dimensions: left, right, up, down, and back and forth. But in order to simplify things, especially at the beginning, we're usually going to be discussing things in 1 dimension. So you may have a line, and an object may be located here, and it might be that this is the 0 location, the 1 meter location, 2 meter location, 3 meter, 4 meter, and so on. So we would say the position would be somewhere around 3.5 meters or something like this. It's telling you where is the object. Along with position is something called displacement, which is basically like how much the position changes. So if an object moves from one location to another location, then it has some displacement. It moves, let's say, from here, it moves over to here. Then there's a displacement of negative 1.5 meters. It moves to the left, negative, a distance of 1.5 meters. So displacement is basically talking about how much a position changes. Well, that leads to another thing we must know, which is time. That's, of course, denoted by the variable t, and that, of course, is the measure of time we will be using. When we discuss things like displacement, we may want to know, well, okay, sure, the object changed position, there's some displacement, but maybe it's important to understand how much was that displacement in a certain set period of time, because of course you could have things moving slowly and you can have things moving very quickly, and the way you differentiate between the two is by, of course, relating the displacement to the time that it took to make that displacement, and that relationship is called velocity. And the variable is v. Notice, this is just for your own knowing, notice how at the end of my v there's this little line. That's just because my v and my u can look very similar if I don't put this little edge on the edge of my v. So especially if I'm writing quickly or anything, don't think that this variable here is an R or a square root symbol. My V's will always have that little ledge off the edge of the V, and that's just so it's easier to tell if I'm writing a V or a U when I'm handwriting stuff. Anyway, the variable V for velocity, we discussed it a little bit when we talked about vectors. Velocity is a vector quantity, and it's the speed of an object, of course, but also in which direction the object is traveling. So, the first big equation we can have, of course, is, well, how do we figure out what the velocity of an object is? Well, it turns out that the velocity of an object is given by the displacement, that is, how much the position changes. This little triangle symbol, delta, means change in. So the change in the position, that's called the displacement, divided by how long did it take to do that, the change in time. And so that makes sense. When we talk about speed, when we talk about velocity, we always say something like, the car was traveling 35 miles per hour. So the unit, miles per hour, is telling you the displacement is so many miles, and the amount of time it took was 1 hour to do it. So that's the unit of velocity. Now for us, the units we need to know when we're discussing physics is, first of all, for position, the unit is meters. This is the metric system. Time, the unit is seconds. Velocity is meters per second. So, if in the course of doing any problems in this class, you're given something in miles or feet or inches or something like that, you have to convert those units into meters and seconds and things like this. When we have a question where that's like that, I'll show you how to do it. It's just a matter of converting. All you need to know is what is the conversion factor. So, it's like 1 kilometer is 1,000 meters. So if you went 2 kilometers, you just convert it by multiplying by 1,000, so you went 2,000 meters. That kind of thing is conversion. All right, anyway, so we have the displacement, we have the position, we have the time, we have velocity. There's one more we're going to need, and that's called the acceleration. And the variable for that is a. And what the acceleration describes is, well, it's possible that when an object is moving, it's moving at a different rate. It's changing its speed over time. There's no reason why when something moves, it always has the same speed. Obviously, when you're driving a car, you're constantly slowing down and speeding up. And the acceleration is the quantity which relates that, which tells you about how much your velocity changes. And in fact, the equation, acceleration, is the change in the velocity over time. And so, of course, looking at this equation, we can see what the units must be for acceleration. Change in velocity, well, that's meters per second. And the change in time is seconds. So that's meters per second times seconds, which is meters per second squared. And that's the units for acceleration, meters per second squared. So these 4 quantities are going to be the quantities which we will discuss, we will relate to each other for the purposes of the kinematics, the study of the motion of objects. And it's only these 4 that we need to know. Everything else falls into place. So when we're given equations, these are going to be the 4 variables that are going to be in our equations. Now, before we get to the big leagues of kinematics, actually discussing the big equations, of course, we should have for sure down this equation and this equation. Those are important to know. But before we do the analytical stuff, working with the equations and doing calculations and things, it's helpful to get a conceptual idea of how these things relate to each other. And the best way to do it is usually graphically, with graphs, to see if I plot certain pieces of information, does that give rise to new information just by looking at this plot? And indeed it does. If it didn't, I wouldn't be discussing it. So the first big type we'll do is what's called a position versus time graph. And what a position versus time graph is literally a graph where one axis is the position. So let's say this is the position, the y-axis, and the other axis is time. And what we're going to do is plot how an object moves over time. And so let's say what we have is something like this. Our first one, we're going to plot, the object starts at the 2 meter mark. So let's say this is 1, this is 2, this is 3. And here's 1 second, 2 seconds, 3 seconds, 4. Okay. And let's say I have a plot that looks like this. Okay, just a nice horizontal line. And I want to see, what does this tell me? What's the story that goes with this graph? And so what you should be able to do is look at the graph and literally read off what's going on. When I look at this, I see, okay, position versus time. So the graph, the function that I graph here, will tell me where is the object located at each period of time. So when I look at this, I say, okay, well, at t equal to 0, so when the first starts, the position of the object is at the 2 meter mark. So that's here, right here. Then, after 1 second, so now I'm here, I'm still at the 2 meter mark. So that tells me I didn't move in that 1 second of time. I stayed at my position. Okay? What else? Well, I wait another second, so now I'm at the 2 second mark. And what's going on? I'm still at the 2 meter mark. And in fact, no matter what time I look at on this graph, I'm always at the 2 meter mark. Well, this tells me I must not be moving, or whatever this object is, let's say. The object hasn't moved. So, the object remains at rest at the 2 meter mark for all 8 seconds. That's the story. Very simple. That also, from this picture, I can get the velocity of the object. I could get the overall velocity, and I could get what's called the instantaneous velocity. So let's say I was asked, find the velocity of the object at the 3 second mark. How would I do it? Well, velocity, I remember, is the change in the position over time. So if I want to see at the 3 second mark, what's the velocity, then I want to know just before the 3 second mark and just after the 3 second mark, how much did the position change? Well, it didn't. the displacement, the change in the position of my object, was 0. And in fact, the better way to do this formally is to say, when one writes change in position, what one means is the final position minus the initial position. Okay? So when I write a subscript F, that means final. When I write the subscript O, that means initial. Sometimes in some textbooks it'll be a subscript I for initial, but you'll find as you go higher up in physics, they usually say things like X naught, that means X sub 0. That means the initial position or initial velocity or whatever. So when one writes delta something, they mean the final amount of that something minus the initial. That's what defines change in a quantity. So when I have delta X for the 3-second mark, I'd say, okay, well, just after the 3-second mark, that's my final position. Where am I? I'm at the 2-meter mark. Minus the initial, well, what's happening just before? I'm also at the 2-meter mark, so that's 2 as well. So final minus initial, I got to 2, and I started at 2, so 2 minus 2, divided by the change in time. Well, let's say from, 3.5 minus 2.5 second mark. Right? So here, let's say that's about 3.5. This is about 2.5. So there's my numbers. 2 minus 2, that's 0. Over 3.5 minus 2.5 is 1. 0 over 1, that's just 0. So that tells me that at the 3-second mark, how fast was my object moving? 0 meters per second. And of course that makes sense if we think about it logically. Our intuition says, well, if the object didn't move the whole time, then it must have had a velocity of 0. Because if it had a velocity, then surely it would have moved at some point. So we can see something here, which is when we have a position versus time graph, the first thing we can do is we can kind of read off the story of what the object is doing. In this case, it was just moving at constant, it was just staying in place, I should say. But the secondary thing we could do is talk about the velocity of the object. Somehow, encoded in a position versus time graph is the velocity. And this is an important thing to note. And in fact, it's easily seen if you think about it like this. If you're given a graph, if you're given a function, there's only 2 things you could do with that graph, other than tell me the story of what the graph says. You can either find the slope of the function, or find the area. Under the function. Right? You're given a graph, there's your line, it may be curvy, it may have kinks, it may be going in different directions, whatever it is. There's 2 things you can do. You can either find the slope of the line or find the area under the line. That's all you can do with it. So, if you're given a problem, then, and you're asked to solve something about that problem, then you know, okay, either I'm going to look at the slope or I'm going to look at the area. So then, once you understand that, all you have to do is ask yourself, what would the slope give me? So let's look at the position versus time graph. Position versus time. So here's position, here's time. Let's say I have something, a graph that looks more like this time. 1, 2, 3, 1, 2. Okay. Well, if this is our new graph for position versus time, what would the slope tell me? Slope. Well, first of all, if you remember from algebra and math class, the slope of a line is the rise over the run, or the change in the y-axis over the change in the x-axis. Okay, fine. But for our particular graph, what is the change in the y-axis? Well, the change in the y-axis is the change in position. And what's the change in the x-axis? Our x-axis here is time, delta t. So now we look at this and we say, okay, is this a quantity we know? And indeed it is. The change in the position over time is the definition of velocity. So this is a big deal. Anytime you're given a position versus time graph, if you look at the slope of the line, that tells you the velocity of the object. What about the other thing? What about the area? Let's see what that does. Area, well, that's going to be the length times the width, right? So what's length times width here? Okay, well, length, let's say that's the height as well. So the length is like delta x, and the width, that's from left to right, that's delta t. Do we know anything? That's the change in the position times the time. Nope, I don't. So that tells me for a position versus time graph, the area doesn't tell me anything. So, given a problem, either I'm going to look at the graph and let it tell me the story. So for this particular graph, it says this object is moving. Let's say in 1 second it has gone up this much, and in the next second it's up to here, and in the next second it's up to here. And if this was drawn accurately, this would tell me that for every second I'm going up by the same amount. Okay? In 1 second I went 0.7 meters. In the next second, I went another 0.7 meters, and in the third second, I went another 0.7 meters, and so on. So that says the object travels in the positive x direction at constant velocity. How do I know it's constant velocity? I look at this line and I see it's a straight line. Straight line means it doesn't have any kinks, it doesn't have a curve, it's just perfectly straight. Perfectly straight lines have constant slope. The slope does not change. If it's a constant slope, and the slope means velocity, then the object has constant velocity. Now, in this case, the slope is some positive slope. It's going up and to the right. It's a positive slope. So that means it has some positive velocity. The previous example, this line also has constant slope. So I know it also has constant velocity. It just turns out that because the slope of this line happens to be 0, that constant velocity is a velocity of 0. So it stayed in place. Here, object has constant velocity, but it's not 0. It's some positive number. If I want to figure out what the positive number is, I look at the slope. So I'd have to make sure my lines and everything are drawn accurately, and I have the data in the table for you to be able to see it. But for now, just understand, all you do is look at the slope. So like I said, let's say this is 0.7, this is 1.4, 2.1, and so on. Then I would say the velocity is rise over run. So that's the change in position over time, which means final position minus initial position over time. And so let's take the 1 second mark, since it doesn't matter where we choose, since it's constant. So in the 1 second mark, I went from 0 up to 0.7. So 0.7 is final, minus 0 is initial. The time, I went from 0 seconds to 1 second, so 1 minus 0. So that's 0.7 over 1, which is 0.7. What's the velocity? 0.7 meters per second. That velocity is constant because no matter where I choose to measure it, it's going to have the same slope. If you don't believe me, let's check it out. Let's look from the 1 to the 2 second mark. So again, velocity is final minus initial over time. The final position, that's at the 2 second mark, I'm at 1.4. The initial 1 second mark, I'm at 0.7. Over the change in time, final time is 2, initial time is 1. So 1.4 minus 0.7 is 0.7. 2 minus 1 is 1. So again, 0.7. We know it has to be the same because we look at the line and it's a straight line. Straight lines have constant slope. Constant slope means constant velocity if the graph is position versus time graph. I think that's good for right now. What we're going to do next time is we're going to try to, given the position versus time graph, can we create another graph which tells us how the velocity changes with time? Of course, this implies that we're going to have position versus time graphs where the position changes. It's not a constant line anymore. The line may have kinks and stuff like, for instance, position, time. Maybe the graph will look something like this. And so, obviously, there's some change in velocity at these different marks here. Here it's constant velocity, but then it changes to this other velocity. Then it changes again to this other velocity, and so on. So for each one of these sections, I could calculate the velocity, and then what I'm going to want to do is plot the velocity versus time that I see from here. So maybe this section, this beginning section in 1 second, I went from, let's say, 0 to 4. Then I would say the initial velocity is 4 meters per second. And then from this part to this part, there's some other velocity. And so I'm going to want to plot what these things look like, for instance. That's what we're going to do next time. And then once we have position versus time and velocity versus time down and how they relate, we're finally going to look at acceleration versus time and how does it relate to the others. Once we have a good idea of how these graphs all look, we can read the graph, we can look at it, tell a story, what's happening to the object. Once we have that conceptual picture, then we can move on to the analytical stuff with equations, because we'll have a good conceptual view of how systems work. The equations will fall into place for us. So I hope this made some sense. Be on the lookout. I'll be posting some practice problems, of course, for this as well. And I wish you luck.